Check 1, 2, 3. Is it loud and clear? Check 1, 2, 3. Is it loud and clear? You can indicate in the chat now. Is the voice loud and clear? Okay, great. just one more voice check because some of them were telling that there was a disturbance. Is that is it perfectly clear? You can put in the chat. Is it loud and clear? You can put in the chat. Huh? One more sound check. Is it perfectly clear? No more disturbances. Somebody can put in the chat. It will be great. Is it loud and clear? What kind of background noise? May I know what kind of background noise? Because there is no feedback from my end. Is everybody hearing clearly? Oh, there's a small zip noise in the voice, no? I will try to sort it out as we go along, but we start work. Yeah, what to do with the right? Good evening, everybody. The small zip noise that you will hear is connected to the clip. I'll try to sort that problem out. Most probably next week. It's still persisting. Right. So you all said there were 3 MCQs which were difficult. So we'll discuss those 3 MCQs. 2015 A-level question comes under hydrostatics. So this question technically is a very good question, not difficult, but you need to carefully understand the concept. Right. So all of you look. 2015 A-level question. Right. A vessel of uniform rectangular cross section with height h0 and mass m contains a certain amount of oil having mass simple m and density of oil as shown in the figure. The vessel floats vertically in water of density rho w, which is much more larger than the density of oil, with height h1 underwater, right? Can you remember a few, not last week or the week before last, the same concept, but in a different way we spoke. Now there's a replacement. You're taking some oil out and replacing it with water. So replacement is taking place. Right. Have a look. So we'll start with basic work. So here you go. Total height h0. Total height h0. Here there is some oil. Color. Oil is there. And it's floating submerged h1 height. Floating submerged h1 height. So even for an MCQ, now a lot of people they won't think the proper order. Now, remember, when you are learning something, there is a process to learn it. You learn it the correct way. If you learn it with shortcuts, most probably what? You will destroy your knowledge. So learn it the proper way. Proper way has no shortcut. Yeah, right. Have a look. Now here, what are they saying? The mass of the vessel is capital M. So weight is mg. Here you have oil. Mass of oil is simple m. Simple mg. They have not given you the cross-sectional area of the vessel. So I will take the cross-sectional area of the vessel as A. A cross-sectional area. Cross-sectional area. So upthrust is acting here. We have to mark it on the same line, but here for the clarity, I'll mark it separately. Upthrust acting on it due to what? So I mark the forces here. Sum of forces in the upward direction balances sum of forces in the downward direction. Sum of forces in the upward direction balances sum of forces in the downward direction. So forces upward, upthrust, mg plus capital mg. Mg plus capital mg. Don't write. Look and wait. I'll give you time to write. Look and wait. Upthrust here, A h1 rho wg, simple m plus capital mg. Simple m plus capital mg. There you go, equation number 1. There you go, equation number 1. Now keep on reading slowly. A certain volume of oil is now replaced. I'm removing certain amount of oil and I'm replacing with water, equal volume of water. Underline this keyword, the maximum volume of oil that can be replaced while keeping the vessel floating. The maximum volume of oil that can be replaced by keeping the vessel floating. Now, how can you keep the vessel floating? By removing and adding maximum amount is by making it float up to the brim. So it's floating in this manner. I will draw it separately. These are happening. Now it's fully submerged. Now it's fully submerged. Height h naught. Height h naught. Height h naught. What I have done is I have removed some oil. I have removed some oil and I have replaced it with an equal volume of water. I have replaced it with an equal volume of water, right? Equal volume of water. So volume of water removed or volume of oil removed is V. Volume of water replaced is also V. So here you have oil. Here you have water. Don't forget, surrounding also you have water. Surrounding also you have water. Now the beaker is just floating. So weight of beaker is there, mg. Now be careful. Upthrust is going to be completely different. Now why has it sunk more? Now you look at this picture and tell me which has a bigger weight. First picture or second picture? Full system, which has a bigger weight? You can answer in the chat. I'm looking at the chat now. Which has a bigger weight? Which has a bigger weight? First picture or second picture? Answer. First picture or second picture? You can put 1 and 2. Which has a bigger weight? Answer. Which has a bigger weight? Which system? Picture number 1 or picture number 2? Quickly. Obviously this one, no? This has a bigger weight. That's why it has sunk more. The object has sunk more. Now let's start thinking why it has sunk more. Because I have removed oil and put water. And the weight of water is more than the weight of oil that was removed. Simple. Clear? So why has the object sunk more? The object has sunk more. Now, if you look at this picture, Domina Hari, carefully think and answer. Now, if I look at this height, this is h0 minus h1. h0 minus h1. Now, by removing some oil and putting some water, equal volume, this has completely sunk. So, what do you think has happened? What do you think has happened? The weight has increased. Simple answer. Right. Has the weight of the beaker changed? No. Then what has increased? Submerged volume has increased. That means there is an additional upthrust. There is an additional upthrust. This additional upthrust is created by additional weight. Now you can see this volume, additional volume has submerged. So additional upthrust, even last time I told you, think about this extra thing. Additional upthrust due to water equals additional weight. Additional weight. Right. So what is this additional upthrust? A h0 minus h1 rho wg is the additional upthrust. That means that here this part was not underwater. Now in the second picture, that part is also underwater. Underwater means because of that additional, there's an increase in upthrust. So the additional increase in upthrust is this part. Additional increase in upthrust is that part only. We are thinking about the increase. We are comparing the first picture to second picture. We are thinking about the increase. Right. So this is the additional upthrust. Now, tell me where did the weight additionally increase? I removed some oil and put some water. I removed some oil and I put some water. Some oil is still there, but I replaced it here. That means whatever you replace is heavier. Okay? Whatever I replace is heavier than what I removed. Understood? Whatever I replace, X was there. I removed X and put Y, it became heavier. And what is the additional weight? Y minus X. X was there. I removed X and I put Y. And it sunk more. Why did it sink more? Because Y is more heavier than what? X. So Y minus X is what? The additional weight. Clear? That means if I write here, additional weight is weight of replaced water minus weight of removed oil. Tell me in the chat, did you all understand this? Did you all understand this? Is it clear? Answer. So why did it additionally submerge? It additionally submerged because the weight has increased. So how did the weight increase? I removed oil and put water. When I removed oil and put water, what has happened? The weight has increased. By how much? I replaced it with Y. I removed X. So Y is heavier than X. So Y minus X is your additional weight. Clear? Right. A H0 minus H1 rho Wg. Water replaced volume is given V rho Wg. Removed oil is V density of oil into G. A H0 minus H1 rho Wg. V common, G common. Rho W minus rho oil, equation number 2. Equation number 2. Yeah. Right. So we have two equations. We have equation number 1 and we have equation number 2. What I'll do is I'll write these two separately. Yeah? Okay. So if I'm writing this separately, A H1 rho Wg, simple M plus capital M G. Equation number 1. Additional upthrust A H0 minus H1 rho Wg Vg rho W minus rho I. See whether I wrote it correctly. H0 minus H1 rho Wg Vg rho W minus rho I. Okay, no? Equation number 2. Keep reading. The initial volume of oil is V0. Then the ratio of V over V0 is initial volume of oil which was there. Initial volume of oil which was here is V0. Initial volume of oil. Okay. If you look at the answers, H0 minus H1 is on top. So what I'll do is I'll take a small chance. I'll divide the second equation by the first. A H0 minus H1 rho Wg divided by left hand to left hand. A H1 rho Wg Vg rho W minus rho oil divided by simple M plus capital Mg. So if I simplify this a bit, A cancel off, rho W, G cancel off. Here also G cancel off. From this I can get a relationship H0 minus H1. H1 here, V there, rho W minus rho oil, simple M plus capital M. From this, I can make V the subject, cross multiply H0 minus H1 simple M plus capital M divided by H1 rho W minus rho I. Okay. Looks a bit okay for now. Equation start. They are asking the ratio VO V naught. V naught is the initial volume. Let me go back. Now this initial volume has an initial weight. It's already given. Initial volume has an initial weight. So initial volume V naught. If I want, I can do it here. V naught. I'll do it like this. Mass of oil is volume of oil into density of oil. Right now, the volume of mass of oil only is same. Volume of oil into density of oil is mass of oil. So V naught is equal to simple M divided by density of oil. Double star. Let me go back here. What are they asking me? They're asking me V over V naught. So my V I have put here. H0 minus H1 simple M plus capital M divided by H1 rho W minus rho I. What is V naught? V naught is M over density of oil. M over density of oil. That is V naught. So I'm dividing by V naught means dividing by, if you want, I do like this. For the ones who are thinking. Okay. This side I divide by V naught, this side also I divide by V naught. Finish now. What is V naught now? H0 minus H1 simple M plus capital M divided by V naught is M over density of oil. H1 rho W minus rho oil. Rho oil goes on top. H0 minus H1 simple M plus capital M density of oil divided by simple M H1 rho W minus rho oil. From this I get V over V naught. Do you have an answer like that? H1 MH1 rho W minus rho oil H0 minus H1 M plus M density of oil. I think there's a printing error in the answer. This should be rho W minus rho oil. In the 2015, what you call original paper, this is rho W minus rho oil. Okay, no? So this is your answer. This is your answer. Seconds even. Okay, no? Yeah. Understood? Is it clear? You can put in the chat if you want. Okay. Right. Write a small sentence. Write a small sentence. Let's write. By removing oil and putting in water, we create an additional weight. We create an additional weight. This additional weight this additional weight will cause the object to submerge more. This additional weight will cause the object to beaker to submerge more. This additional weight will cause the beaker to submerge more. And the additional upthrust is equal to the additional weight. And the additional upthrust is equal to additional weight. Okay. Right? Once you need it now, write down carefully. Once you need it, write this down carefully. Quickly write, huh? Quickly write. Quickly write down. Quickly write down. Okay, next one. Next picture. Additional upthrust due to water equals additional weight. Then you can divide the equations and work around it. Quickly write. Right? So here Star divided by double star. Star divided by double star will get you your answer. Okay. Two 2015 A levels was anyway a very odd year. The questions you have to think a lot and do. So yeah. Even the next question is a 2015 question. Finished? Right. 2015, this question was also given. I'm sure some of you all could not do it. So mainly because, you have to be a bit careful when you do it. They have given a small cut sphere. We call it truncated because it's cut there at the bottom. Here, from the center to this, the length is L. Here you can say radius is R. Here you can say radius is R. So what's happening is they have told you something very important. An object in the shape of a truncated solid sphere. Truncated means cut somewhere in the middle. Truncated solid sphere is kept at the bottom of a tank as shown in the figure. The distance from the center of the sphere to the bottom is L. Now the tank is slowly filled with water. Assume that the truncated sphere is fixed to the bottom. Fixed. If it's fixed to the bottom, now tell me, is water touching the bottom? Tell me. If this part is fixed to the bottom, is water touching the bottom? Water is not touching the bottom. If water is not touching the bottom, if you go, you should remember, resultant upward pressure force is your upthrust. Resultant upward pressure force is your upthrust. That means top and bottom liquid should be there. If bottom liquid is not there, upthrust is not there. Understood? Yeah. There should be at least a thin layer of water touching the bottom. They have said this is fixed. Fixed to the bottom means there is no thin layer of water underneath. Therefore, there is no upthrust acting. Okay. So if you look at your theory book, you will know resultant upward pressure force means up and bottom liquid should be there. Resultant upward pressure force is your upthrust. Understood? Right. This is taught in theory. Now here this is fixed. Fixed means bottom there is nothing, but only around. That won't give upthrust. Everywhere you should have water, then only will give up. Right. Now let's look at this carefully. Here, let me mark water. I'll mark water with red color. Here you go. We are filling this with water. So I'm focusing on these locations. I'm focusing on the center line here. Below the center, above the center. Okay? Below the center, above the center. Right. Look at this very carefully. Now, when it's here, look at this carefully. There is a curved part here. You can see that there's a curved part. Remember, pressure forces will always act perpendicular to the surface. Pressure forces will always act perpendicular to the surface. All right, here we go. Colored there. Let's say from the surface. Let's say from the surface. There is a certain depth. So the pressure force acting there will be perpendicular to the surface. Pressure force acting there will be perpendicular to the surface. I'll name it F. Remember, when you're finding the pressure force there, you must find the distance to that location. Distance to that location, you can see is a very small distance, so very small force. From this source, if I look at very carefully, you have a particular angle. let's say theta. If I take component F1 cos theta and here vertically F1 sin theta. So on this surface here, there will be a pressure force acting in that direction. Here F1 cos theta, here F1 sin theta is there. Look at this carefully. Yeah? What about the other side? Same. This is 3D, okay? If I look these two sides, it should be around as well. Right. Here also same location, same force will act perpendicular to the surface. Horizontal, let's say theta. F1 cos theta is acting. F1 sin theta is acting. What can you say about F1 cos theta, F1 cos theta? They will cancel off. Remember, it's a 3D object. F1 cos theta, 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 F1 cos theta. All the F1 cos thetas will cancel off. Only F1 sin thetas are acting where? In the upward direction. Okay? Because the upward force has a sin theta variation. Because the upward force has a sin theta variation, the variation is going to be a curve, or not a straight line, but a curve. Okay. Any doubts you can ask? Any doubts? Is there a doubt? Any doubt? No, no? Right. Don't write anything. Keep looking. Huh? Now look at this. Now look at this. Now we increase the level of water. Truncated surface. Center here. Center here. Let's say we have come to the center. Water level is at the center. Water level is at the center. Okay. Center means L. Now you can see this is your curved surface. This is your curved surface. Here also this is your curved surface. Still the curvature, if I mark it clearly, somewhere here now the depth has increased. Here the depth was very small. To this point the depth was very small. Let's say x dash. Now somewhere here perpendicular to the surface, we can find the resultant location F2. Angle is alpha. Resultant here is F2. Angle is alpha. F1 or F2 cos alpha. F2 cos alpha. And F2 sin alpha is acting in the upward direction. F2 cos alpha and F2 sin alpha is acting in the upward direction. What can you say here? Again, F2 cos alpha will cancel off. F2 sin alpha will what? Be acting upward. So from here to here, you can see your resultant force is varying in the form of what? Gradually increasing, but it's not a linear curve. So if they are asking you the variation of upward force, F is upward force. They are asking you the variation of the upward force with length. So from 0 to let's say L. 0 to L. Is L no? From 0 to L, how the variation is. You can see force has increased. How can the force increase? The depth has increased. X double dash. Here x dash, here x double dash. Here also similar location, x double dash. So the depth has increased, so the force has increased. Has the force increased linearly or non-linearly? Non-linearly. Why non-linear? Because there's a sine alpha variance. Sine alpha variance. Yes. I'm not going to draw for now. I'm just going to keep it there. So in your head, you also think. If there was no water, it's nothing, no upward force. Now at L, of course, there is upward force. But the upward force is varying according to sine alpha, sine variation. Sine variation means in the upward direction, force is increasing, non-linear, not linear, non-linear increase. So it's a non-linear increase. Non-linear increase. Clear? Okay, no? Non-linear increase. Right. Then look at this carefully. Now, truncated bottom, half level. Now let's say the water level is slightly above. Slightly above. Slightly above. Now look at this carefully. Bottom curved part is here. Bottom curved part is here. Has the force increased? Yes. Force has increased. But now this part is curved in the opposite direction. I will show it with a different color. I hope you can see this. Can you all see this color? Green color, can you all see? Can you all see the green color? Lightly you can see, no? Lightly you can see, no? Right. Okay. Look at this carefully. Here, perpendicular force F3. Here also perpendicular force F3. Here let's say angle beta. Here angle beta. F3 cos beta. F3 cos beta. F3 sin beta is acting upward. F3 sin beta is acting upward. F3 sin beta is acting upward. Now be careful, okay? I will show here this depth is x triple dash. Slightly increased. Now look at this. This curve surface, force there is F4. Again with the horizontal, if I take theta dash, here it's going to be F4 cos theta dash. Same way here, F4, angle here theta dash, F4 cos theta dash, F4 sin theta dash. Here F4 sin theta dash. Right. Now again, F4 cos theta, F4 cos theta, they cancel off. Cos components cancel off. If I take this depth here, it's smaller. I'll take it as y. Early x dash, x double dash, x triple dash. Now here y dash. You all tell me, Vilu, what can you say about the resultant upward force? Resultant upward force here, if I look, F3 sin beta minus F4 sin theta dash. Clear enough? Upward forces minus the downward force. So has your upward resultant force increased or reduced? When I go just beyond the center mark, has the upward resultant force increased or reduced? Reduced. Guaranteed reduced. So here, F3 sin, F4 sin theta dash on one side. Everywhere, same story. So F3 sin beta minus F psi, that means the curve, it's still a curve, but the resultant has reduced. Resultant has reduced. So here, if I consider it upward force 0 to L earlier, Now slightly more than L. I think they are given the curve L to 2L. L to 2L. So as it's increasing, what's happening? F3 is also increasing. Why the depth is increasing? No? Depth is increasing. V is also increasing, but reducing. This is larger than this. Larger, smaller, but different. Little by little, when water increases, V is also increasing. So looking at this, what can you say? Looking at this, what can you say? If I come to this position, if the water level comes to this position, here L plus R, what will happen? What will happen? L plus R, what will happen? But before L plus R, we will say 2L, double L, because they are given that location as a special case. So here, double L, double of L, somewhere here, double of L. Now what's going to happen? Now what's going to happen? Look at this. Again here, upward, again here, upward. Upward force is there. From here, downward. From here, downward force is there. If you look at this, from here to here, larger, here to here, larger upward force. Here to here, it's smaller, so smaller force downward. Larger force upward, smaller force down. Then it's going to completely submerge. Huh? Completely submerge. Completely submerge. This level. Now from the center, L plus R. L plus R. Okay. Now start looking at this carefully. Yeah? Start looking at this carefully. Right. So let's go back. Don't be in a hurry. Let's go back. Here there is upward force varying in the sine form. Varying in the sine form means it's going to be a curve. F sine theta forces are increasing. So the more the water increases, F sine theta increases. Up to L, it will be a curve, almost like a sine curve. Now sine graphs are like this, no? Reducing graph. But here it's increasing, no? So it's an increasing graph. Increasing graph. Right. Increasing graph. The increasing graph, I'll go like this. Right. Up to L. Beyond L. Beyond L. So up to L. So beyond L is L. Huh? Beyond L. Now the force starts to reduce. Now still the depth is more. This is more. So the difference is getting smaller. This is more. This is also more. This is more. That's also more. Little by little, water is increasing. This is increasing. That's also increasing. Difference is gradually reducing. Still, this is bigger. Then the curve will be in that direction. No? Then the curve will be slightly like that. Going in that direction. Going in that direction. L to 2L. Slightly increasing, slightly reducing. Like that. Slightly reducing. Once it's equal like this, then what? Maximum upward force, maximum downward force, minimum downward force. Here L technically to the bottom, larger depth, larger. Here smaller. Smaller means what happens? Resultant force in the upward direction becomes maximum, almost maximum. Now what happens here? Look carefully, yeah? Look at this carefully. Now it's fully completed, fully closed, fully closed. When it's fully closed, look at this carefully, yeah? When it's fully closed, it's fully filled. Fully filled means this. Now what can you see? From here to here, larger, here to here, larger. But don't forget, now there will be a force acting in that direction as well. Now the angle comes into play. These are most people don't realize. Here you have a force. Here you have a force on this part. On this part. Resultant force. Here you have a force perpendicular to the surface. Here you have a force perpendicular to the surface. First components cancel off, only sine components are there. Sine components are there. Look at this carefully. First components cancel off, sine components are acting downward. Sine components are acting downward. Carefully look. They have given you here, guaranteed R is going to be larger than L. R is going to be larger than L. So R is going to be larger than L means downward forces are larger than upward forces. L means upward is more than downward. Now once it goes there, yes, the depth is large, but here the downward force generated is more. Why is it more? Have a look. This part here, have a listen. First sine. Here you have first and you have sine. This part here, upward forces are there, depth is large. Yes, depth is large. Depth is large, depth is large, depth is small, depth is small. But now there's a downward push because R is larger. R is larger. So here you have a curve, here you have a curve that way. Now you must think about the remaining part. Remaining part is going to be what? R plus L or L plus R at the surface. At the surface and beyond. Right. Before that, let's write this down and go with. I hope you understood this first two parts. Very important. First two parts. Here, gradually, when the water is increasing, resultant upward pressure force increases. Here, it's increasing in the sine format, so it's going to be a curve. Let's write that. Let's write that. Draw it, Viru. Let's write. Gradually, when the water increases, 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 the horizontal pressure forces will cancel out. The horizontal pressure forces will cancel out. The horizontal pressure forces will cancel off. But the vertical pressure forces will remain. But the vertical pressure forces will remain. But the vertical pressure forces will remain. The vertical pressure forces vary according to sine component. The vertical pressure forces vary according to the sine component. Therefore, it's a non-linear increase. Therefore, it is a non-linear increase. Therefore, it is a non-linear increase. Okay. Carefully draw these to understand it's going to be sine variation and then draw this curve. So it's from 0 to L, 0 to L, 0 to the center point. It's going to be a non-linear increase. Carefully draw it quickly. Draw it quickly. Okay, right. Now tell me, I want you to think and tell. It's a very good thinking question. When this is truncated, the volume touching water, is it compared to the top? Top is like a ball, like an aluminium bowl on top. This bottom part. What can you say about the volume touching water? The volume touching water at the bottom here, and compare this volume. You can see this volume here is more than that volume. No? Understood? This volume on top is more than the volume at the bottom because one part is missing. There, one part is missing. Understood? So the volume of water touching the bottom here is less than the volume here on top. Understood? There, the volume or the space of volume of water touching the bottom here is less than that. Here one part is not touching. Here around it can touch. Okay. Right. Clear? Go to the next one. Now from here it increases. So, till the curvature is downwards. You can see now upward force is there, larger depth, upward force is there. Again, downward force is also there, but upward force is more than downward force, but the resultant will reduce. It will keep on reducing. The resultant keeps on reducing until it reaches L and L. Until it reaches L and L, right? Then this volume, look at this, the volume touching the bottom and the volume touching the top are what? Same. Understood? This question is a marvelous question for many reasons. The volume touching here and the volume touching there become equal. So from here, larger height, maximum upward force. Here, smaller downward force. So the resultant force in the upward direction is maximum there. Understood? Here, smaller volume here, larger volume there. Here, larger upward force. There's a downward force. So you have a larger resultant force acting where? Upward. Maximum. Maximum. And when it goes beyond this, you can see this additional part is also there. So the downward force starts to increase. Because the volume of water touching the curve surface on top now is more. Here the volume and there the volume are same. Larger depth, smaller depth, larger resultant force, maximum upward force. Maximum upward force. Is it clear? Look at this picture. Volume at the bottom, volume at the top. This volume and that volume are same. So larger upward result, maximum upward resultant force. Now when this part also comes, the top part has larger volume. So the force acting downwards is more. So the resultant force now acts there. The upward resultant forces start to reduce. The upward resultant forces start to what? Reduce. Yeah. Tell me if you have any doubt. Ask. Think about the volumes and tell me. Think about the volumes and tell me. Is it clear? Is it clear? Huh? We have Nada, we have Akira, Anna, Vinod. Any question? The volume here, the volume touching the bottom here, L, and when it comes to 2L, the volume touching there. This volume and that volume are equal, symmetrical. So the upward resultant force will be maximum there. When you go beyond this, the downward volume or the volume touching the top surface increases. The space where the liquid touches increases. When there is more space where liquid touches, there is more spaces where downward force will act. Understood? Here, equal locations, here also equal locations. Equal locations here, equal locations there. The moment it increases there, on top there are more places for it to act. Because that part is missing here, no? That part is not here, no? If that part was also there, then we can say up and down are equal. But that part is now not there. So when it goes beyond this, there is more spaces for locations for, there is more locations for pressure force to act. More locations for pressure force to act means more force were acting in the downward direction. Is it clear? Answer me, Will. Is it clear? One person said okay, Nada said okay. What about the others? Understood? The volume here and the volume there, same. So same space location here, same locations there. The moment volume increases, bottom there is fixed locations, less location. Here now there is more locations for the water to touch. More locations means more pushing downwards. More pushing downwards means downward force will increase. Clear? Downward force will increase. Downward force will increase. Perfect. Downward force will increase. Now downward force increases, you tell me. When downward force increases, this is upward resultant force. Huh? Upward resultant force. Upward force will start to reduce. Upward force will start to reduce. After L plus R, reduce. After L plus R, it will reduce. After L plus R, it will reduce. So far so good. Answer 1 is wrong. Answer 2 is wrong. Answer 3 is wrong. Answer 4 looks okay. Answer 5 also looks okay. So yeah, our selection is between 4 and 5. Huh? Our selection is between 4 and 5. Selection is between 4 and 5. Right. We have one more part now. More than L plus R. More than L plus R. When it increases more. Now when it increases more, what happens? You can tell me. Now I want you all to think. I have done majority of the thinking, majority of the talking. You all tell me now. Once it is here, what can you say? Once it is there, what can you say? Now what? Now more than L plus R. No? Now more than L plus R. More than L plus R. Now what? From here to here, the depth is more. Here to here, the depth is more. But now, upward force is there. From here onwards, beyond this level. Beyond this level. Beyond this level. What happened? Up to this level, more places are there now. Now, for those more places, the force is increasing linearly. H rho g is increasing. H rho g is increasing. So linearly, H rho g is slowly water is being put. So linearly, the force is increasing downwards. Linearly, the force is increasing downwards means from here also the height, if you take, height is more. But here now the force is increasing more space here, less volume there, more volume here on top, more places pushing it down, more places pushing it down. It's increasing linearly. So if you take the resultant upward force, here it's acting upwards. So F sine theta 1. Here it's going to act downward, but there are more places now. F sine theta dash downward. Now, more places having greater pressure means this will start to increase. This will start to increase. These only few places. Few places it's increasing. More places, more pressure is increasing. This will start to increase. Downward will start to increase means it's going to increase linearly. Like H rho G effect. Now beyond this, the number of places fixed. Now when H increases according to the force will increase. Force will increase means linearly it's going to increase. Force is linearly increasing means the resultant force will linearly reduce. Understood? Again, I tell. Now this was your sine and cos, no? Right. Sine and cos was there. Now what has happened? Now what has happened? Now there is an upward force here, this curve. Here there is a downward force. Downward. Here to here, full curvature downward. Curve downward. Full curvature upward. Full curvature upward. Right? From here, when it starts increasing, downward forces have increased. How? Linearly. H rho G times area. Force. So the downward forces start increasing linearly. Then the resultant force will start to reduce. Also linearly, right? Beyond this, there is no extra shape. Here, what reduce shape, 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 shape. Then from here onwards, it's going like a box only volume is increased. Like a box only volume is increased. Like a box volume is increasing means now it's going to reduce linearly. Why linear reduction? Because beyond this height, water is going to adapt linear increase in volume. Linear increase in volume, linear increase in pressure force, linear increase in downward pressure force means the resultant pressure force in the upward direction will also start to reduce. Is that clear? Beyond this, there is no more small volume, big volume. Everywhere is fixed. So now when H increases, the downward force. Now this is like keeping an object like this and increasing water. When H increases, the downward force will increase. Now this is not touching the bottom, so there can't be upward force. Now the downward force will increase. How is that? Linear increase. Because when H increases, H rho G A will also increase. Bottom is not touching with water. So here, there will be a linear reduction. Is that clear? Is that clear? Understood? Beyond the height, it increases as H rho G. Understood? Beyond this, there is no additional curve to get. Beyond this, it's increasing. So downward pressure force has increased linearly. Downward pressure force has increased linearly means the resultant force will also reduce linearly. So I'll come again from the beginning just to complete this. So from here, when the liquid increases, this space here is curved. There's an upward force. Where is it? Sine theta. It's going to be increased with sine theta. From there to there, it's going to be an increase. Beyond this, when it goes, now there's from a bottom space and a top space. Bottom volume and top volume are equal. One instant, upward resultant force will be maximum. Now, when it goes beyond this, there is more space for the pressure to act. Now, these are equal spaces, equal volume. Beyond this, more volume. More volume means more downward force. More downward force, again curving. So, there's a reduction in the upward force. There's a reduction in the upward force. Beyond this, when the volume increases, there's going to be a constant push. Constant push. When H increases, constant push acting downward. So the resultant force will reduce in the upward direction linear. Because when H is increasing beyond that curve, everything is completely covered. No? Beyond that H, AH rho G. Then 2H, 2H rho G. 3H, 3H rho G. So the constant linear increase in pressure force. So linear downward increase in pressure force means upward will cancel off. Resultant downward pressure force, somewhere it can be zero as well. Okay, no? Linear downward, linear. So therefore your correct answer is going to be answer number 4. From your selection of 4 and 5, because beyond this it's going to be a constant increase. Downward pressure force will increase linearly. So resultant pressure force downwards also increases linearly. There you go. The correct answer is answer number 4. So I hope these 2 questions in 2015 A level, now you understand it. So it's good. Remember, we have big plans for Helpline. We'll keep on discussing these kind of difficult questions, and then we will improve on this as well. I will tell you all about this as we go along. You come to the class, I'll tell you. Okay. Right. Okay, then enough for today. I hope you all will look through these questions back again. If there's any doubt, you can of course clarify it. Okay, then. Stay home safe. Keep working.